Welcome to the EF5 Advanced Training, Module 1.2, Distributed Parameters. This is the Advanced EF5 Training from the University of Oklahoma, the Hydrometeorology and Remote Sensing Group. My name is Laura Labriola. Let's begin. So you have just watched the ensemble output presentation, and now we'll be moving into distributed parameters. For this training video, we will be reviewing hydrologic models. We're going to be reviewing distributed parameters. We're going to look at the distributed parameters in EF5. We're going to set up EF5 so that we can upload those distributed parameters, and then we're going to go through an example. So from the Foundation EF5 training, Module 1.2, we talked about the water cycle and how it is portrayed in hydrologic models. In order to utilize these models, computers use grids and cells to organize the input and to run an algorithm. And so we can actually take this figure to the right and divide the area we want to model into cells. So this is the type of hydrologic models that we can use. In each process of the water cycle, there are factors or settings that govern how the process works. And we talked about all of these kind of parameters: hydrologic conductivity, the roughness of the land surface, the equation of the storage capacity curve, or the Vic curve, and there are many more factors that contribute to the water cycle. These are called parameters, and adjusting them can make a simulation or our model more or less accurate. And we can change these parameters in a process called calibration, which we did in the last training video. You can also review calibration in the original or Foundation EF5 training, Module 2.2. So now we're going to talk about the types of hydrologic models. If I can adjust these parameters for each model cell independently, that's when you have a distributed model. And we can see it from the figure to the right. It's the map that has all the squares in it. So what that means is for each square, we can have an individual set of parameters for what the land is like or what the Vic curve is for that individual grid cell. So if you have a set of parameters in a few spots over a river basin, you usually have a semi-distributed model. So it's not as fine resolution as our distributed, but you still have parts of your river basin that you can say is different than other parts of it. Lastly, if you have a set of parameters that are constantly for the entire area of your basin, then you have a lumped model. And that's something that we've been working on throughout this entire EF5 training through the Foundation and the Advanced. We say that for the entire river basin, those parameters have one constant value. And as we know for the water cycle and for the land, it's not constant throughout. Land varies and rainfall varies. And so it's helpful to use distributed models because we can model different cells independently. So in the training so far, we have used the one constant set of values to describe a basin, and that's the lumped model. While these do give useful results, we assume the parameters are constant for the entire area, which is usually not true. So by using the distributed parameters, it allows the user to input parameters for each model cell and actually show and model the true identity of the river basin. So now we're going to be talking about distributed parameters. Distributed parameters can improve results compared to lumped parameters, or those continuous values over a river basin. With lumped parameters, the value of the parameters is the same over the entire model domain. And in this case, we're talking about the river basin. However, we know that soil properties, impervious area, channel cross-sectional area, and other properties of the land vary from place to place. However, with EF5, it has the ability to use distributed parameter grids so that we can independently model the land variability of the river basin. You can think of these distributed parameter grids like a DEM, an FDR, or FAC that we've seen before. But instead of topographical grids, each grid contains parameter values for every grid cell. The advantage of this is that it allows us to represent land variability. However, the disadvantage is that it's very complex to calculate the values as well as to use them. However, it's easy to use in EF5. Parameter grids, when available, are stored in the params folder of a particular EF5 project. So in previous EF5 examples that we've run, we have about 5 different subfolders. We have basic, we have precip, we have observations. Now we're going to be adding something called the params folder, and this is where you'll store your distributed parameters. Regular lump parameters can still be used. That's when you have the constant value of a parameter. However, when you add params to it, then it will be interpreted by the model as multipliers applied to the distributed parameter grid. And we'll look at this a little bit later. So for example, we have a parameter called FC. So if that was 0.3, the FC parameter grid would be multiplied by 0.3 at each location. So using distributed parameters, you might wonder what parameters can be made distributed. So there's several parameters that are used in the CREST model that are made distributed. We have the fractional impervious area, we have maximum soil water capacity, we have the saturated hydrologic conductivity, we have variable infiltration curve exponent, we have overland alpha, and then we have channel alpha and beta. And those might sound familiar from previous EF5 parameter trainings we've done. So all of these parameters from the CREST water balance model are available in distributed parameter grids. So to use distributed parameters, we want to make sure the grid is of the exact same size, resolution, and extent as the topographical files. In CREST param set and KW param set, those are 2 blocks that are used in the control file. What you can do is add _grid to the end of each parameter name, and then you would put that equal to the file path to either an ASCII or TIFF grid, and that would activate the gridded parameters. So for example, we have a parameter called WM in your control file. So if you put WM is equal to 150.0, it might become this instead. You would write out WM_grid equals, and then you would put the path to the distributed parameter grid that you have. In addition, you could leave the WM parameter, and then that's what the multiplier is that we talked about previously. We would say WM is equal to 1.0. And by saying this, it's telling EF5 to use the exact grid, the exact distributed parameter grid that we inputted with no multiplier. We're saying that we trust our distributed parameter grid completely, so EF5 can just use that parameter for WM for your whole river basin, and that would be it. However, if you know that the values are off by a little, you can use this multiplier to change those. So we're going to look up how to set up the control file. So what you would do is that you would go to your CREST param set in your KW param set, and then you would add grid to the end of each parameter name, and then the file path to a .asc or .tiff grid, and that would activate the gridded parameters. So for example, to the right of this slide, we see the control file, and we see the 2 blocks, the CREST param set and the KW param set. These are the distributed parameter grids that we supply you in the EF5 training. So what we have is we put all of the parameters. We have WM_grid, and then we have a file path name. And we have the same for our IM_grid, FC_grid, and B_grid. Below that, we put the gauge that we want to use the distributed parameters on. And below that, we have the multipliers. So we're saying that we're going to use all of these parameters, WM, B, IM, KE, FC, and IWU, as we're going to use them exactly as they are. IWU we don't have distributed parameter grids for because that's just part of the warm-up. But for the first 5 parameters, we do have the distributed parameter grids, and we use just the one multiplier of them. We use the exact values that they have. For the KW param set, for the kinematic wave, we have the alpha, beta, and alpha naught as grids. So we only put underscore grid for those 3 parameters. So first, let's review what we know about EF5's parameters. We've talked about this in several EF5 trainings in the past, so if you need a refresher, please find that video in the EF5 Foundation training. So overall, there are about 13 of EF5's parameters when you use crest and the kinematic wave. And these are divided into those 2 categories. Remember from our last training, crest is a water balance model. And so for these crest parameters, it's how water is partitioned and accounted for in each cell. For the kinematic wave parameters, this is the routing model, and that affects how water is routed from cell to cell. And as we've seen, some parameters affect the model results more than others. So we've seen that WM, B, alpha, beta, and alpha naught are generally the most important when calibrating a model, but others can be too. So for the crest parameters, we're going to do a short review just to refresh what they are. So WM is the maximum soil water capacity. B is the exponent of the variable infiltration curve. IM is the impervious area ratio. KE is the conversion factor from PET to actual ET. FC is a soil saturated hydrologic conductivity. And IWU is an initial value of soil water, a percentage of WM. So in the example to the right, we have the Wing 2 example that we did in the previous video. And those are the lumped values. We're saying that for the whole river basin, those parameters are constant throughout it. So WM is the maximum soil water capacity, the depth integrated pore space of the soil layer in the model in millimeters. So this is how much water the soil can actually store. Usually this is a function of several soil properties. So you can think of this logically. As you increase WM, we're saying that there's more space in the soil for water, which means less runoff will be produced. And we can usually say that this number lies between 5.0 and 250.0 millimeters. We have the parameter B, which is the exponent of the variable infiltration curve. And so we talked about the variable infiltration curve in our original EF5 training. And what it does is it governs how much water enters the soil layer and how much remains at the surface as runoff. So logically, we can think as you increase B in value, you tend to produce more runoff. And usually B lies between 0.1 and 20. The next parameter that we'll be discussing is IM, which is impervious area ratio. So you can think of this as a percentage of area of your model domain that's covered in an area that can't be penetrated by water. And so this, you can think of this as roofs, concrete, rocky soils, and other impervious materials where water can't be absorbed. So as you increase IM, your runoff would increase. Usually we would say that the range would be from 0 to 0.5. You generally do not want to manually calibrate the IM because it is fairly easy to observe from surveys or remote sensing. So if you know about 10% of your basin is covered in rocks or concrete, your IM would be about 10% or 0.10. We also have the FC parameter, which is a soil saturated hydrologic conductivity, and this is in millimeters per hour. This parameter describes how easily water moves through saturated soil. So the higher the value you have, the more easily water can travel through saturated soils. The higher values of FC tend to decrease runoff. And this number can be determined from soil properties and field measurements, which can help reduce the possible range of values in the calibration process. So FC can range from 0 to 150. So we just reviewed all of the CREST parameters. Below on this slide is a summary of the water balance parameters, the names of them, the recommended ranges, and a brief description of their sensitivities. So this is something we talked about for each parameter. For example, for impervious ratio, we said as we increase the value, we're saying that water can't be absorbed as easily. So we're going to have less infiltration and more runoff as we increase impervious ratio. We're also going to briefly talk about the routing parameters that we're going to be using as distributed parameters. We'll be using the kinematic wave routing scheme. And the way you set this up in your control file is under the KW param set block. We have 7 routing parameters in EF5. We have TH, which stands for threshold, and this is the number of grid cells needed to flow into a cell for it to be part of a channel. We have under, which is the interflow flow speed multiplier. We have leak I, which is the amount of water leaked from interflow reservoir in each time step. We have ISU, which is the initial value of the interflow reservoir. We have alpha and beta, which is included in the equation for stream flow, which is equal to alpha multiplied the cross-sectional channel area raised to the beta. Finally, our 7th parameter is alpha naught, and this is the alpha value that's used for overland, not channel routing. We have an example of how the kinematic wave parameters look in a control file. So to the bottom right of our figure, we have the control text file for our Wing Chun example. We're briefly going to be talking about the parameters that we can make distributed in EF5. So we have alpha, and that's a multiplier in the equation stream flow is equal to alpha multiplied by the cross-sectional area raised to the beta. And when we hold a constant A, stream flow, and beta, as we increase alpha, this slows down the flood wave. And what that means is that the hydro peak is actually delayed. And usually alpha can vary between 0.01 and 3.0. The next distributed parameter grid that we have is beta, and it's the exponent in the equation. Stream flow is equal to the cross-sectional area of multiplied by alpha raised to the beta. So when you hold a constant A, Q, and alpha, when you increase beta, your flood wave slows down. So beta can vary between 0.01 and 1.0. Finally, the last distributed parameter we will be using is alpha naught. And alpha naught is a multiplier in the equation. Stream flow is multiplied by alpha times the cross-sectional area raised to the 0.6. And we use alpha naught to govern routing for overland cells. It behaves the same as the channel alpha. But note that in overland cells, instead of the beta value, it's always set at 0.6. And this value can be found by solving Manning's equation. And we usually have a range of alpha naught that varies between 0.01 and 5.0. So we're going to go over a little bit about what we have for you in this advanced EF5 training folder. So if you take a look into your EF5 Advanced and you go into examples, Nizoya, params, you should see a folder like this. We have CREST, inundation, and KW. And these are the distributed parameters that we've supplied for you. We also have an inundation grid files that we will discuss in our next video presentation. So just to briefly look at what parameters we have WM for Africa, but we will also supply for the entire world. These are the distributed parameter grids that we'll be using for our example in this presentation. We have K-set. We have impervious area ratio. And we also have B. We also have the kinematic wave distributed parameters. So we have this zoomed in for the Nizoya River Basin, which we'll be doing our example on, but we will also supply the whole world's distributed parameters. So the important thing to think about when we look at these distributed parameters is how, even just looking at the pictures, how the area varies, even just over a little bit of area. And so that's why it's helpful to use these distributed parameters. Over a specific area, we can have completely different values for the same area that is better shown through these distributed parameters. Finally, we have alpha naught, and all of these were specific to the Nizoya River Basin. An important part of this as well is if we can use calibration with these distributed parameters. So now that we have the values for most of the parameters needed for crest and kinematic wave modeling, we can perform automatic calibration to figure out the best values to calibrate the model with. So the next slides will guide you through how to perform automatic calibration with distributed parameters. But first, we're going to do a quick review of the automatic calibration in EF5. So adjusting parameters individually is called manual calibration, and that's a time-consuming process that requires active involvement. It can be time-consuming, and it's really hard to know if you've actually reached the optimum set of parameters. However, with automatic calibration, we are able to solve these problems by using a computer program that searches the available parameter space using a single objective function and the hydrologic model. So what this means is that it uses EF5 and it calculates the simulation using parameters that it randomizes, and then it sees if the model evaluation indices got better or worse. So it uses a stream algorithm, and this is discussed in the EF5 Foundation Training video 2.2 if you want to look into this further. But pretty much what this is, it's a global parameter optimization method. And it uses something called machine learning to see which values are better and then which values are worse. And so the objective function choices that we can use in EF5 include Nash, correlation coefficient, and the sum of squared errors. So DREAM algorithm stands for the Differential Evolution Adaptive Metropolis. And what this does is it tunes scale and orientation of proposal parameter distribution using differential evolution. And it takes full advantage of distributed computer networks, so it makes it pretty fast to run. So we have this graphic here to kind of show you what this means. So in our first box, we have all these randomized dots, and these have numbers. They're at an x1, x2 location, and we say, let's see how we have parameters. What the model does then is that it creates proposals. And so it left some of the dots, so it completely changed the dots, the places of them. And it says, do these numbers work better with the model or not? Then it will go into the third process where it will either accept or reject the placement of those. And so as we can see, the brown dot did not change. So that means that in the second proposal, in the second step, it didn't have a better score. So it went back to its original place. And that's kind of what the EF5 DREAM algorithm does. So the DREAM algorithm requires parameter ranges to search. So picking good ranges is important. And we looked at these ranges in our last video. These ranges are a soft limit when doing manual calibration, but a hard limit for automatic calibration methods. So we need these ranges to tell the model how low and high to go. However, your ranges can't be too big, or you require more function evaluations to properly search the parameter space. So this means if you have really high values, it's too much for the computer to actually look for a valid number. However, ranges can't be too small, or the parameter space may not be large enough to yield good objection function results. So this means you may be missing the number if your function is too small. Hydrologic model parameters do influence each other, so our problem space is underdetermined. So the example that we'll be working on today is using distributed parameters over the Nzoia River Basin in Kenya, which is upstream of Lake Victoria. So before we start, what will we need for our example? We're going to be using 90-meter DEM, FDR, and FAC files that we will create. We'll be using those distributed parameter files that we showed a few slides ago, and we'll also be preparing our control text file. So in order to download this fine resolution data, we can find this at earthexplorer.com. To download these files, you'll need a free account to access the data. However, we've already included this data set in your data folder. These are just some instructions just in case you want to try to download this for yourself. So what you'll do is you'll highlight the desired area that you would like data from. From here, you'll click Data Sets, which is in the bottom left picture with the red box around it. Next, you're going to be led to the second picture on the right, and you're going to expand the title called Digital Elevation. Under that, you're going to see another title called SRTM, and you're going to expand that title. And then you're going to click SRTM Void Filled. So now you're going to download your data. For this example, we're only going to need 9 tiles that surround the region of our interest. And you'll be able to download is when you look at the picture as we have on the bottom left figure. And then we have on the bottom right, we have a zoomed in version. And what it is if you look at the red box, there's a download button. And you can click that and you can pick which one to use. So you'll typically take the TIFF version. Okay, so now we're going to start our computer version of this example. So when you're ready to start the computer part of this training, go ahead and click on QGIS Desktop 2.6.1. I already have it loaded, so I'm going to go ahead and start this training. If you need extra time, feel free to pause the training and resume when you're ready. So what we have are 9 files that we downloaded from Net Explorer, and they're all located in your EF5 Advanced Data Net Explorer folder. So since we have 9 TIFF files of the Nzoia River Basin, what we want to do is merge them together. And you can see an example of this in the presentation slide. We see we have 9 tiles, and then we have a blue arrow, and we have 1 tile of the entire river basin. And we're able to do this through QGIS. So let's go ahead and put the data together. To do this, you'll want to go to your toolbar, and you'll see Raster, and you'll select that. You'll then scroll down to Miscellaneous, and from there you can look to the right, and the second thing is called Merge. So you'll go ahead and click that. From there, you're going to select. You're going to click the first select of Input Files and press Select. So for me, my Net Explorer file showed up immediately, but just to show you, what you're going to do is you're going to find your EF5 Advanced folder in your wherever you put it on your computer. So for me, it's on my desktop, so it's easy to find. So I'm at my desktop. I see my EF5 Advanced folder, and I double-click that. I then am going to go to Data. Then from here, we're going to go to Net Explorer. And here are where the 9 tiles are. So you're going to go ahead and select all of these files. So you can either highlight them or drag your cursor over them all to select them. Next, you'll press Open. From here, we're going to go to Output File, and we're going to press the second Select icon. So what this does is that it's going to take all 9 files as our input files, and it's just going to output one file. And we're going to call this one Nizoya_merge.tif. We'll press Save. And then the last thing before we press OK is we're going to check No Data Value. And we're going to change the 0 to -32768. And what this means is that if there are any data values that aren't available in this TIFF file, then it's going to make that a number of -32768. So we'll go ahead and press OK. So I got this error message that says this process crashed sometime after starting successfully, but that's okay in this case. So I'll press OK, and then we're going to press Close. So you won't have anything on your QGIS screen now, but if you go ahead and navigate to your EF5 Advanced folder, and you go into Data, and you go into Net Explorer, we can see Nizoya Merge ended up in the folder. So next what we're going to do is we're going to go back to the EF5 Advanced folder, and we're going to start this example. So we're going to go to Examples, Nizoya, and now what we're going to do is we're going to create a QGIS_Nizoya folder. So you can do this by right-clicking on your screen, going to New, and then going to Folder. And we're going to call this QGIS_Nizoya. Once we have that done, we're going to navigate back into our EF5 Advanced folder. We're going to go into Data. We're going to go into Hydrosheds. And then you're going to see a zipped folder called AF_RIV_30S. So what these contain important QGIS shape files that we want to use. So we're going to have to extract this into a folder that we can use. So what you'll do is you'll right-click and click Extract All. And you might get this pop-up. We actually want to extract it into the folder we just created, the QGIS and Zoya. So how we can do that is if you press Browse, I'll go back to my desktop because that's where I put EF5 Advanced. You'll find your EF5 Advanced folder. You'll navigate to Examples, Nizoya, and then you can use your QGIS Nizoya folder. And so you'll say Select Folder. And so your destination should look just like mine from the EF5 Advanced down. So you'll go ahead and click Extract. And then that folder will pop up, your QGIS and Zoya, and you should see files that look just like this. So you can go ahead and exit out of these. And you're going to go back to your QGIS. So what we're going to do is we're going to go to Layer, Add Vector Layer. And then we're going to press Browse. If I can make this. Yeah, we're going to click Browse. We're going to navigate to our EF5 Advanced, Examples, Nizoya, our QGIS Nizoya folder. And we're going to select AF Riv 30 S shape and press Open. Oh, I clicked the wrong one. So we're going to go to Add Layer, Add Vector Layer, Browse, and you'll want to make sure that we're opening the correct shape file. So if you open up your screen a little bit more, you'll see Type. And I accidentally hit the HTML file first. So what you want to do is you'll want to find the SHP file and go ahead and open that and press Open. So you'll see something pop up on your screen, just like mine, the whole continent of Africa. So what we're going to do is we're going to actually, all of these are rivers that make up Africa. So what we're going to do next is we're going to filter out large rivers. So in the layers box, in mine, it's on the right-hand side, but in most QGIS, it's on your left-hand side. What we're going to do is we're going to select features using expression. So what this is we're going to highlight the AF _ Riv _ 30S like it is on my computer screen. Then we're going to go to this icon where it has a backwards 3 or a sigma and then a sticky note next to it. So we're going to go ahead and click that. And then you should get this pop up. So from here, we're going to scroll down and double click Fields and Values. And then you should get, that should expand. So then what you'll do is you'll double click Up Cells, or you can type this in yourself. Then we're going to put is greater than 800. So what we're doing is we're finding larger rivers that have an attribute of up cells greater than 800. We're going to press Select, and then we're going to press Close. And so my QGIS has changed. Instead of it all being one color, we have green and yellow. And what that means is all these yellows are rivers that are greater than 800. So what we're going to do is we're going to clip and filter out these rivers. So the first step of this is you're going to go to your layers column, and you're going to right-click your AF _ Riv _ 30S file. From here, you're going to right-click and press Save As. From here, we're going to go, we're going to keep the Esri shape file. And for Save As, we're going to click Browse. And then we're going to navigate to the QGIS Nizoya folder, which we're already in. And we're going to call this large _ rivers .shape. And press Save. We also want to make sure we're checking this box or putting an X on it where it says Save Only Selected Features. So what that is doing is it's selecting all of the yellow rivers that were larger than 800, and it's only saving those features. We're also going to change the extent of our layer, and we're going to crop it to our area. So for Nizoya, we're going to change north to 2. We're going to change east to 36. We're changing south for -1, and west will be 33.5. So once your pop-up looks like mine, you're ready to press OK. So what this looks like is if you untoggle the larger one, we'll have a little box over here. And those are all the large rivers that are in the Nizoya River Basin. So now that we have our large rivers for the Nizoya River Basin, we're going to create the outlet shapefile for it. In order to do that, we're going to go to our toolbar, and we're going to go to Layer, Create Layer, New Shape Layer File. So we're going to keep it as a point. We're going to name it Nizoya.shape. And we're going to press OK. And then we're going to save it into our QGIS Nizoya folder, and then name it again Nizoya.shape. And press save. So now we have a dot on our layer column. From here, we're going to turn on toggle editing, which is this pencil in the third row between the project and the edit columns. So it's this pencil right here that says toggle editing. We're going to go ahead and click that. We're then going to zoom in into the area of 34.087 and 0.120. And we can see this in the coordinate box that's on the bottom of the QGIS window. So what we're going to do is we're going to click on the magnifying glass, and we're going to hover to wherever we're close to 34.087, and then 0.120. Okay, so it's over here. Let's see. So we'll want to get familiar with how to move the cursor around. So we said it was 34.087. 0.087, and then we also said that it's at 0.120. So I'm at 34.087. So we're somewhere around this for our outlet. So we're somewhere on this river. So what we'll do is, now that we know where the general area is, we're going to go back to that pencil where it is, and we're going to go 2 over where it says Add Feature, and we're going to go ahead and press that. We'll then highlight the place where the outlet is about, which is right here, and we'll go ahead and click that. And then for ID, we'll press 1 and press OK. So now we have the Nizoya River outlet right there. We're going to go ahead and clip the DEM now. And in order to do that, we're going to have to go into our Nizoya merge. So we're going to toggle off this pencil, and we're going to press Save. And we're going to zoom out a little bit to see the whole river again. So from here, we're going to go to Layer, Add Raster Layer, and we're going to go to our Nizoya merge and press Open. So now that we have the Nizoya merge here, we're going to go to Raster, Projections, and Warp with parentheses Reproject. And here we're actually going to be able to clip the DEM. Oh, but the DEM. So we want to clip the DEM just a little bit. Since we had 9 tiles, they went a little bit bigger than we want to. And since this is fine resolution, we want to get the file size as small as we can. So we're going to pick some nice round numbers to clip the DEM to. So we're going to say that the left side is 33.5 degrees east, 36 degrees east, and then the upper edge is going to be 2 degrees north, and the lower edge is -1 degree north. So we go to Raster, Projections, Warp, Reproject, and we get this pop-up. So we have Nizoya merge already in the input file, so we're going to leave that. Next, we're going to click the second select for the output file. We're going to navigate back to our advanced folder. We're going to go to examples, Nazoya, and we're going to find that QGIS Nazoya folder. And we're going to save it in there. We're going to name it clipped _ raster.tiff. And we're going to press save. Then we're going to make a few more edits on this pop-up window. We're going to keep source SRS for this projection. We're going to put an X on resampling method, and we're going to leave it to near. And then we're going to do the same thing with the node data values. And we're going to enter -32768. And that's all we need to do for this upper portion. Next, we have to change a little bit on the bottom column. What we want to do is we want to click the pencil icon below Load into Canvas when finished. So we'll click this pencil. So that means we can type into this bottom box now. So what we're going to do is after -R near, we're going to type right after it 33. We're going to type in -TE, then 33.5, -1, 36, 2. And we did this in the Foundation EF5 training. And what this means is that we're clipping it to those dimensions. And -TE is actually the extent of the raster that we're going to create. And it's in the order of left, bottom, right, and top edges. Once we're done with that, we can go ahead and press OK. And I get processing completed, so I'll go ahead and press OK, OK, and then close. So now I have my clipped raster, and if I unclick my Nazoya merge, we can see that gets a little bit shorter. So you can go ahead and click on Nazoya merge, right click, and remove that DEM, and press OK. We can also move large rivers above clipped raster, and we can see that our rivers coordinate with our DEM now. So next we want to fix the DEM. When we change the resolution of a DEM, we tend to break things, and that's from the model's perspective. We create something called pits or sinks that didn't exist in the original data because we changed the resolution to it. So if you had done the EF5 Foundation trainings, you would have installed Towden. So we're going to be using that toolbox next. So what we'll do is we'll locate the processing toolbox, which is on the right-hand side of my QGIS screen. And we're going to go to Recently Used Algorithms, and we can find Pit Remove first. So I'll go ahead and double-click Pit Remove, and then I'll make sure that Clipped Raster is in the Elevation Grid option. From there, I'm going to click the 3 dots below Pit Removed Elevation Grid, and then I'm going to press Save to File. I'll navigate back to my EF5 Advanced, Examples, Nazoya, and my QGIS Nazoya folder. And I'm going to change the name to corrected _dem.tiff and press Save. All that's left is press Run. And so when this process is done, it just closes its window, and then it's already in the layers box as Pit Removed Elevation Grid. The next step we want to do is we want to convert the rivers. So what we want to do is our goal is to burn our rivers into the corrected DEM to make sure the model knows where the streams are for sure. To do this, we can go to the raster menu on the toolbar. We're going to go down to conversion. Then we're going to go to rasterize, parentheses, vector to raster. So what we'll do is we'll select our input file, and we'll want to do large rivers. Next, we're going to click on the select for output file for rasterized vectors. And we're going to call this rasterized _ rivers.tif and press save. So I get a pop-up when that happens, and this is fine. You can just press OK for this. The next step we're going to do is we're going to go back into the box on the bottom and press the pencil so that we can edit this box. What we want to do now is we want to delete everything from -A to the last 3,000. So everything that I highlighted, we're gonna delete. Once we delete it, we're going to type in -burn space -10 -TE, then 33.5, -1, 36, 2, -TR, 0.007, 0.007. So everything we just put in is a computer code, pretty much. So our first word that we typed in was -burn. So what it is, it's calling to say we're going to burn a river, right? We're gonna say remove the elevation by -10. So what it's going to do, it's going to take whatever pixel the river is in, and it's going to write the number -10 for every pixel in which a river occurs. And then we have -TR, which is the extent and resolution, as a DEM we already created. So once this box looks like mine, you'll go ahead and press OK. So you'll get processing complete. You can go ahead and press OK, OK, and close. So if you go ahead and toggle off some of the layers, you'll see your rasterized rivers, and it should look something like this. So the next step is we're going to take this rasterized river file that we made, where every part where there's a river, it has the value of -10. We're going to add that to our DEM. So we can go ahead with burning our river. We can do this by going to the raster toolbar. We're going to click raster, and we're going to click that first option, raster calculator. From here, we're going to click the 3 dots for output layer, and we're going to go ahead to our EF5 Advanced Nizoya QGIS folder, and we're going to type in burned _DEM.tif and press save. We can leave everything else as it is, and we're going to go down to the raster calculator expression box. From here, we're going to click on it. We're going to go to the raster bands, and then we're going to double click on the pit removed elevation grid at 1. So go ahead and double click that, and it will show up into your raster calculator expression. Once that shows up, we're going to type in plus. We're going to put in a left parenthesis and a right parenthesis. We're going to multiply that by 3. Now what you're going to do is you're going to go in between those parentheses. You're going to click in between them, the 2 parentheses, and then you're going to go to your raster bands and double click rasterize rivers. So now that we have a valid expression for our raster calculator expression. And so it should look something like this. Once it does, you can go ahead and press OK. And now we have a burned DEM that that added the -10 values of the river. So wherever there's a river, we made that elevation, we lowered the elevation of each pixel in the river channel by 30 meters because we multiplied it by 3. So what this is called is burning the rivers into the DEM. And it makes it easier to model the stream flow of the river. So we want to also use pit remove one more time on our burn DEM. So go ahead and go to the pit remove and double click it. We're going to keep the burn DEM option as our elevation grid. We're going to go to the pit removed elevation grid and click on the second 3 dots icon and go to save to file. And we're going to call this one DEM.TIFF. So what this is our last DEM. This is the final DEM that we're going to use in our model. Go ahead and press save, and then press run. So what showed up on my layers is the pit removed elevation grid. So this is our final DEM.TIFF. So what you'll want to do is you'll want to find the older one that we did from earlier. You'll want to remove this layer. So you can do that by right-clicking and press remove. So now that we have our DEM.TIFF, we're ready to make the DEM derivatives. So we're going to do this by going to our processing toolbox. Then we're going to go to D8 flow directions and double click it. So you can either click your pit removed elevation grid, or if you're not sure if you removed the right one, you can click the 3 dots and you can actually access the DEM that we just created and press open. From here, we're going to go to D8 flow direction, and we're going to click the 3 dots and go to save to file. And we're going to name this one flow_dir.tiff and press save. We're going to keep this X over open output file after running algorithm. And then for D8 slope grid, we're going to uncheck it so there's no X there. Once you've completed that, you can go ahead and press run. So once the run completes, you should get an output that looks like this. However, you can see how fine the resolution is just at this scale. You can see every bit of difference in this compared to lower resolution FDRs that we've created before. So in your case, if you were using QGIS and your computer crashed and it can't produce these images because they're high resolution, we have a solution. So if you go into your EF5 Advanced folder, so it's on my desktop, EF5 Advanced, into your examples, Nozoya, we've created QGIS_Nozoya_advanced folder for you. And it has all the files that we're creating with this presentation, just in case your QGIS doesn't have the capacity to do it. So we're going to go ahead and move on, just in case you do want to follow along to create high-resolution DEM derivatives. From here, we have our flow direction, and this is what it should look like. However, in order to read this into EF5, we need to convert this to a format that EF5 can read. In order to do this, we're going to go to raster, conversion, and then translate, and that's in parentheses convert format. From here, we're going to make sure our input layer is flow direction. We're going to go to output file, and we're going to save this as fdr.tiff. And this will be in our QGIS and Nozoya folder. We're going to go ahead and press save. And then we're going to just leave everything the same. but we are going to scroll down to our load into canvas when finished, and we're going to press the pencil to edit it. So from here, we have, it says GDAL_translate. And what we're going to do is we're going to get rid of -OFGTIF. And we're going to delete that. Instead, we're going to type -OT space capital F for float 32. Once you have that typed in, you can go ahead and press OK. And once that processes, you can press OK, OK, and close. So now we have our FDR, which is an EF5 format and is the DM derivative that we will be using in EF5. The last step is that we need to create our flow accumulation grid. So finally, we're going to create the last DM derivative. In order to do this, we're going to go into our processing toolbox, into our TAUDIM, and find D8 contributing area. And go ahead and double click that tool. From here, we're going to make sure that we have the correct D8 flow direction grid. So in my case, it says burn DM, but I'm going to select the FDR. From here, you're going to check for edge contamination. We don't need that. What we do want is the D8 contributing area grid. So from here, we're going to click the last three dots icon, and we're going to go save to file. We're going to make sure we're in our QGIS_Nozoya folder, and we're going to call the file name fac.tif and press save. We're going to go ahead and click run. Once your D8 flow direction grid has run, you'll get an output that looks like something like this. And this is your fac.tif. So what this means is the lighter the color, the more cells that are contributing to the flow at that point. So this is the flow accumulation grid. And what we really want to look at is the gauge point. And so in our presentation, you can see it in the red box, and it looks like the river flowing into it properly, and that follows the path of the original river shapefile. So let's see how well the Nozoya outlet that we created is. So I'll go ahead and make sure it's at the top of my layers and that it's on top of all of them as well so that we can see it on top. Now I'm going to press the magnifying glass with the plus sign, and I'm going to create a box around the Nozoya outlet so I can see it clearly. I'm going to zoom in a little bit more. And so it kind of looks like the box is over the river. So that's pretty good. So now we're actually going to check see how well the flow accumulation grid actually is. And we can do this by using the Identify Features tool in QGIS. We can find the icon between the database and the web toolbar. It has a circle around an eye, and then it has a pointer pointing to it. So we're going to go ahead and click that. And once we click it, we're going to click the gauge point. And instead of clicking Nozoya outlet, we're going to click on FAC instead. Okay, so instead of clicking if we zoom in more, we can actually see where the outlet is supposed to be on the river. So as we zoom in, we can actually click on the river cell that it's actually on. So once we click this, we're going to click FAC, and we get Identify Results column that pops up, or a box. And it says it has the FAC and it has the value of it. And so it says that a lot of cells are flowing into this grid cell. And so we say that about each grid cell is about 90 meters. So if you follow the presentation, if we multiply, this big number by 0.09 kilometers, and then we multiply that again by 0.9 kilometers, we get a number that's close to 11,979 kilometers squared. And that is really close to the Nizoya River Basin, which is about 12,696 kilometers squared. So since these values match pretty well, this means that our DEM, our FAC, and our FDR are ready to go. The last step that we want to do is that since we have our DEM, our FDR, and our FAC files, we want to copy those into our basic folder. So what we're going to want to do is we're going to minimize our QGIS. We're going to navigate into our Nizoya example folder. We're going to go into QGIS Nizoya or QGIS Nizoya Advanced if you weren't able to get all the files created on your own. So we're going to pick out our DEM, our FAC, and then our FDR files. And we're going to go ahead and copy those. You can go ahead and copy this dem.tif.aux as well. It's header files for when you open them in QGIS. Those usually ends up popping up too. So once we have those copied, we're going to go back into our Nizoya folder. And we're going to go into Basic. And we already have 3 files here that we've provided you as well. These are low res, so that when you calibrate, you don't have to calibrate with really high resolution DEM derivatives. You can just use the low resolution. So we're going to add to this folder. We're going to right click, press paste, and now we have all of the DEM, FDR, and FAC in our basic folder. You can go ahead and delete these .tif.aux. So now that we have a neat folder for all of our basic files. So now we're going to go back into talking about distributed parameters. So now that we're preparing our example and we've created the DEM derivatives, we're ready to learn on how to use the distributed parameters in our control file. So we're going to use the distributed parameters in the CREST param set and the KW param set by adding _grid to the end of each parameter name and then the file path to the grid name of it that activates the grid parameters. So we mentioned this earlier. For example, for your WM parameter, we're going to put instead of having WM is equal to 150.0, it might become something like this. WM_grid is equal to, and in our case, params/WM_Namibia.tif. And then we can also add another WM below that by adding WM is equal to 1.0. And that would tell EF5 to use the exact distributed grid with no multiplier. And as we discussed, we could scale these grid values up or down by specifying some other number than 1.0. So this is how we're going to prepare our control file. Go ahead and open control.txt in examples, Nizoya, and distributed example. We're going to go to our precip forcing, PET forcing, gauge, and basin blocks are ready to go. So what do we need to do? We need to tell EF5 about our parameters, instructions for how to calibrate them, and instructions on how to actually run the model. So we're going to go over the blocks just to review. So our basic block. This is the block that will show where the basic files are relative to the control.txt file. So we just created our basic files and put them into the basic folder. However, since our basic files are in the previous directory, we can put .. into that file path, and that will tell the EF5 program to find the basic folder in the previous directory. Next, we have the precip forcing block. So this block contains information similar to our previous examples. And it also has the .. precip folder syntax. So we're saying that the location of the precip folder is one directory ahead of this. Same as our PT forcing. Finally, we have our gauge information ready for this control file. So this is where we have to change things for the distributed parameters. We're going to scroll down to our CREST param set Nizoya. We named it Nizoya, but it can be anything you want as long as you use this same name later in the task block. So this needs to match the name that we put in the task block. We have the distributed parameter values for WM, IM, SC, which is also known as KSAT, and B. We will fill in these by adding _grid to the end of each parameter. We set the parameters equal to the path name to the file, and we end it with TIFF because these are the distributed parameter file types we have. And you can see the example of it in the to the right of this slide. For example, we have WM_grid. We have that .. because it's a directory before. Then you can find those in the params folder, then in that CREST folder, and then you can find it at that file location, wm.tiff. Under all those parameters, we also want to make sure that we put the gauge that we want to apply those parameters to. And then next, we have all of the CREST parameters that we're going to use as multipliers. So in this case, we're putting all the gridded parameters equal to 1.0, meaning that telling EF5 to use these exact grids of the distributed grids with no multiplier. So this means it's using it exactly the values as they are on the grid. Next, we're going to change our KW param set control file. Again, this one is called Nizoya, but if you wanted to rename it, you can, as long as you reuse the name to match it in the task block. Next, we have the distributed parameter values for alpha, beta, and alpha naught. So what we'll do is we're going to do the same thing as above in our CREST param set, and we're going to add _grid to each of those parameters, and then the path to the directories they are located in. And again, gauge should be the same as the gauge block that we've already established earlier in the control text file. So in this case, it's Rwambwa as our gauge name. After that, we're going to put all of the kinematic wave parameters that is associated with the model. And then so we have under, leak eye, threshold, ISU, alpha, beta, and alpha naught. So as we can see, only alpha, beta, and alpha naught are 1.0. The other ones are multipliers of, the other ones are the actual static lumped numbers that we're going to have to keep constant throughout the entire river basin. We have a guide for automatic calibration strategies. So when we use, these are the suggested default ranges for distributed parameters of CREST and kinematic wave. So for CREST, we have the distributed parameters for WM, B, IM, FC. And we recommend to use these ranges from 0.01 to 2.00. So we're saying that the grid is fairly accurate with the numbers that they portray, but they might vary by a certain margin. And we account for that for all of the distributed parameter grids. So we want to be able to use calibration because we're not saying the distributed grids are perfect. So we can actually calibrate by using these small ranges and seeing how to change the multiplier. So when we use automatic calibration on distributed grids, we're actually going to calibrate on the distributed parameter multipliers. And we have this set up for you. So we're going to create a new block for CREST Cali params, which is the CREST calibration parameters. We're going to name this one Nizoya. We're going to keep the same gauge as before. and we're going to put objective. And so you may remember this from the last video, and we usually use Nash because we usually want to maximize the Nash of our simulation. We then put the 6 CREST parameters that are listed for the distributed parameters, where the number before the comma is the minimum end of the parameter range to be tested by DREAM. And then the number after is the maximum end of the parameter range. So for WM, B, IM, KE, and FC, we have the parameter ranges ready. For KE, since that's the kinematic estimation, which is a multiplier, that doesn't have to be in the range exactly, since it's on a distributed parameter grid. And same with IWU. We don't have a distributed grid for that, so we can leave those as the suggested ranges from the previous automatic calibration recommendations. We have 0.1 to 2. However, the values could range from about 5 to 10, depending on your calibration results. So if you're not getting high Nash values, you can change these values from 0.1 to 5 if needed, or even 0.1 to 10. Next, we want to create a KW Cali params for our kinematic wave parameters. We're going to keep the block name as Nazoya. We're going to use the same gauge, Rwambwa. Then we're going to list the 7 routing parameters, where the number before the comma is the minimum end of the parameter range to be tested by DREAM, and the number after is the maximum end of the parameter range. So for kinematic wave, we have the 3 distributed parameter grids for alpha, beta, and alpha naught. And we see that we have the ranges for those as 0.1 to 5. But for the other parameters that we don't have distributed ranges for, we keep the recommended automatic calibration ranges that we've discussed in previous trainings. Finally, we need to tell our task block that we're using distributed grids. So what the job of the task block is that it tells EF5 what to do with the topographical, forcings, parameters, and location information we've given it. So we've named this one Run Nazoya, and we're doing a simulation, so we can see that by the style is equal to SIMU. We're also telling it to use CREST. We're also using the kinematic wave for routing, and then we're using the Nazoya River Basin for the basin. We're using preset from TRIM. We're using the PET but from FuseNet. And then we put our output as our output folder that's located in the distributed example folder. The next is the param set and the routing param set, which is telling EF5 which parameters to use. And then we finally establish a time set. So we're going to go ahead and run this. So what you can do is you can right-click in some blank space in your examples and select New and Text Document. So you're going to create your batch file. If you didn't feel comfortable creating a batch file, you can always go into the software folder, right-click and copy EF5_64.exe, and then paste that into the folder where your control file is. You can go ahead and either double-click the run EF5.batch file, or you can double-click the EF5 executable and run your file and run the model. So if you've done all that, you can actually log into Jupyter Notebook and upload the time series that was outputted. So I've done that for you, and we're assessing the result. So what happened? Our observations are the black dots, and our simulation is the blue line. So what happened is the Nash isn't very good. It's -17. The bias, though, is really high. It's almost 300%. And we can kind of see that in the hydrograph below. We can see that the timing of the flooding is pretty spot on, and the correlation coefficient shows at 0.80. However, that bias is so high that it's throwing off all the other numbers. So that means we might have to use a smaller multiplier of the values from the distributed parameters. Our distributed parameters are a little bit too high and are showing much more runoff than is actually happening. So what we're going to do is we're going to calibrate for better model evaluation indices. So what we're going to do is we're going to rename our old time series as ts.rhomba.crest.old. So what you'll do is you'll go into your folder, you'll locate your output folder, you'll double click it, and you'll find your Excel document for ts.rhomba.crest. Go ahead and rename that to old. And that way, when we run the simulation again, we can actually compare the old values to the new values. So now it's time to calibrate. Since our values, our model evaluation indices, weren't as good as we want them to be, we can calibrate for this simulation. Since we already have our calibration parameter blocks in our control file, all we need to do now is create a second task block to tell EF5 to calibrate. So what you'll do is you're going to copy the original task block and paste it below it to create a second task block as shown in the right. So all I did was I copy and pasted it below the original task run to Zoya. Don't forget, if this video is going too fast, you can press pause and then resume when you're all caught up. So now we're going to edit the task block. First, we're going to rename it. So instead of run to Zoya, we're going to name it calibrate to Zoya. We're going to change the style to Cali Dream, and that means it's going to calibrate it with the Dream algorithm. Next, we're going to add 2 lines below routing param set. And we're going to call them Cali param is equal to Nazoya. And then we're going to do another one called routing Cali param is equal to Nazoya. And what this does is that it says it's called Cali param, and we're naming it Nazoya. And what it does is it finds that Crest Cali params block, and it uses those ranges to calibrate. Finally, we're done with that task block. All we need to do is go to the execute block, and we're going to create a new task, and it's going to be called task equals calibrate Nazoya. You're going to want to comment out or use a hashtag for the task equals run Nazoya line, because if you don't comment it out or just erase it, then it won't run a calibration. It will only run the simulation. Finally, you will want to make sure that you enter one more time after the task equals calibrate Nazoya line, because the program needs one more blank line underneath the control file. So if your EF5 doesn't run, make sure you go back into your control text file and you press enter on the last line. And then go ahead and save this. You'll go ahead and run your EF5 model by either double-clicking the run EF5.batch file or the EF5 executable. As you saw yesterday, the first time you calibrate on a new example, you'll get a warning, which is failed to preload file output. But this can be ignored, and once you run it again, you won't get this error. As Dream runs, your status updates will appear in the EF5 window. So normally it would take about 20 to 30 minutes to run this calibration on your own, so we've provided the calibration output for you. You can go ahead and go into your output folder and open cali_dream.rhomba.crest 14 to 16. And so this is for the years 2014, 2016. The second to last column, which is N, shows the Nash values at each iteration. So the Nash value, as we scroll through the Excel document, we see that it climbed up to 0.5, which is a lot better than -17, which was our earlier Nash value. So this is a review from the video that we did before this, but what you can do is you can take the parameters that are that gave us the Nash value of 0.5 and copy those into your control file. You'll go ahead and paste them into you'll paste your new calibrated parameters into the CREST param set and the KW param set blocks of your control file. Remember, these are the ones with the static values. You don't want to do them for your CREST Cali params or your KW param, Cali params task blocks. You want to make sure that you're pasting these into the CREST param set and the KW param set blocks of your control file. These are your new multipliers that we're going to be using. So if we look back, they all range between 0.01 and 2. So finally, once you have the calibrated values in your control file for the multipliers, you're going to remove the comment or the hashtag from the Run Nazoya line of the control file. And then instead, you're going to comment or put the hashtag in front of the Calibrate Nazoya line. This is going to tell EF5 to run the simulation of the Nazoya instead of calibrating. Go ahead and save it, and then run EF5. So for assessing the result, you can follow the instructions from the original EF5 training modules 1.2 and 1.3 to open up the EF5 output from the calibrated simulation and calculate the skill statistics and produce a hydrograph. Instead of doing this, you can also use the EF5 analysis through Azuri notebooks to automate it for you. So our Nash, we already knew this from DREAM, climbed from -17 to 0.51. Our bias also improved from 7% from 284%. So remember how high the simulation went compared to the actual observations? So now our bias is a lot lower. However, our correlation coefficient dropped to 0.73 from 0.80. We can visualize this through the Azuri notebooks. So you'll follow this link, https://notebooks.azuri.com. You'll click sign in the upper right corner, and then you'll enter your username and password. It will bring you to a page that looks like this. And you'll go ahead and click on the blue box for EF5 analysis, which I highlighted in a red box for you. What you'll want to do is you'll want to upload the simulation that you created. So to upload your own files, you'll click the plus new on the top line of the screen. And then a pop-up will appear. It will say add items to library. So you'll go and you'll press from computer and locate the directory of the CSV file you want to analyze. And so just to make sure you know where everything is, in this example, you'll go to your EF5 Advanced folder, you'll go to Examples, you'll go to Nazoya, you'll go to Distributed Example, and then you'll go to the Output folder. From there, you'll choose ts.ruamba.crest.csv. You can go ahead and open your Python notebook. You'll replace the name of the time series, and then you'll get something that looks like the bottom right graph that we have on this presentation slide. So our new hydrograph is at the lower right, and the old hydrograph is at the lower left. So originally we had a 17 Nash by just using the distributed parameters as their own. We said we completely trusted them. We had an almost 300% bias, and we had a pretty good correlation coefficient of 0.80. However, when we actually calibrated the multipliers, how much of the distributed parameter values we wanted to use, we were able to better calibrate the model. So we ended up having an 0.51 Nash value. We had a 7% bias, and then we had an 0.73 correlation coefficient, which was a pretty good estimator. However, if you wanted to get those values better, you can run Dream again. So usually this means setting the Dream end draw to a higher value, like 3,000. So now when you run EF5 again, and don't forget to change your execute block to change the hashtag from calibrate Nazoya to run Nazoya. You'll want to open your calibration output once the routine finishes, and this might take a long time, but you might have a higher value of Nash. So just to go over some calibration conclusions, 0.5 was a pretty good result, but in operational applications, we would probably seek something nearer to 0.8. Of course, we'd also want to use a warm-up period and calibration and validation periods. So these terms are pretty important to use. A calibration period is the period over time which the calibration is conducted. And so in our example, we did it over 2014, 2016. But then we would want to do a validation period. So this is a different period over which you run the model with the calibrated parameters. So we're saying that we had a pretty good Nash value for 2014, 2016. What if we ran it from 2014 to 2018? How good would our Nash still be? Usually, but not always, the validation period will have worse statistics than the calibration period. There's definitely advantages to using distributed parameters. They allow us to represent land variability. So land variability can change drastically over a few kilometers, and so it's best to actually represent that through distributed parameters. It also allows for easier automatic calibration. Since you're not doing such a wide range of values, we're only doing 0.1 to either 2 or 5 or 10. Thank you for joining us for the Distributed Parameters Module 1.2. Our next module will be Precipitation Forcing. You can follow along in your EF5 Advanced folder in your presentations directory. Thank you again, and I hope you enjoyed the presentation.